Hi, I'm Emma from Team Equilibrium, and I'm here to help you understand the concept of equilibrium so you can knock AP Chemistry out of the park. Equilibrium is a condition of a reaction where the concentrations of the products and the reactants of that system remain constant over time. Just as a roster lists your players and their positions, so too does an equilibrium expression. Your players are listed in your equation. Their positions are listed in your equilibrium expression. Now notice that the equilibrium expression is written the concentration of your product over the concentrations of your reactants. Also notice that each concentration is taken to the power of its coefficient. Remember that only gases and aqueous solutions, not pure liquids and not pure solids, are written in an equilibrium expression. What is K? K is your equilibrium constant. Your equilibrium constant is like your game plan. It changes depending on your players. Here are some common equilibrium constants. We calculate K from the concentrations of our products and reactants. Here's an example. First, let's write an equilibrium expression. Now, let's plug in the concentrations of our products and our reactants. Finally, let's plug into our calculator and solve. What if we have an equilibrium constant, but need to solve for the concentration of one of our products or reactants? Let's use the same equation as before, but instead of solving for K, solve for NH3. We'll also change the concentrations. So, now N2 is 0.399 molar, and H2 is 1.197 molar. K is the same K that we just found. 6.02 times 10 to the negative second. Now we can solve for the concentration of NH3. Once we plug in our calculator, we'll see that the concentration of NH3 equals 0.203 molar. Before, when I mentioned several different equilibrium constants, you may have noticed Kp, the equilibrium constant for the partial pressures of gases. Kp works exactly in the same way as K, except it relates to the partial pressures of gases rather than their concentrations. However, there is an equation that relates Kp to K. Here we see that Kp equals K multiplied by R, the gas constant, and the temperature in kelvins to the power of delta N, the change in moles. Let's do an example. Here, we have a reaction that has taken place at 25 degrees Celsius, or 298 kelvins. This reaction also has a Kp of 1.9 times 10 to the third. The change in the number of moles, delta N, is the number of moles of product minus the number of moles of reactant. So in this case, delta N would equal 2 minus 3, because there are 2 moles of NO2 and 1 mole of Cl2. Or -1. Kp, as we've already stated, is 1.9 times 10 to the third. We're solving for K. We've stated that R is our gas constant, 0.0821, and T, the temperature in kelvins, is 298. Now, when we solve for K, we get K equals 4.6 times 10 to the fourth. What happens when the players on a good team make an error? The other members of that team step up to reduce the error. When a stress is placed on a system at equilibrium, like the players on a good team, the system works to reduce that stress. Now, let's look at this exothermic reaction. If we increase temperature, the reaction will shift in the direction that is endothermic. Because this reaction is exothermic, its reverse reaction is endothermic. Because of this, the reaction will shift to the left, producing more reactants. What if we remove some of the reactants, lowering their concentration? Equilibrium will shift to produce what was lost, so it will shift to the left and produce more reactants. What if we add more of the reactants and increase their concentration? Equilibrium will shift to produce more products to balance out this change. Therefore, equilibrium will shift to the right. What about a change in pressure? If we increase the pressure, the reaction will shift to the side that produces fewer moles. We can tell the number of moles by the coefficients of the products and reactants. Therefore, equilibrium, if we increase pressure, will shift to the right, because there are 2 moles on the right compared to 4 moles on the left. Now you know all about equilibrium. You're ready to step up to the plate in AP Chem and take a few swings at equilibrium yourself.